Okay. Okay. I'm on mute, right? Are you? Okay, cool. Hmm? Okay, so we are going to continue with the quick review of linear algebra today. I think that last class we just started the iterative methods. So any questions from what we saw last week? Remember yeah. Sorry. Oh, okay. Yeah, I just mentioned that. So assignment 6 isn't posted. It's going to be combined with assignment 7. So it's going to be probably posted tomorrow or Thursday almost. So it will be just 6 and 7 together. Okay, and the reason is because we didn't cover much practical applications yet. So yeah, I hope that got good news. Yeah. Okay, so we did a very quick review of linear algebra last Thursday, and we are going to continue this very shortly, and then we are going to move into the applications themselves. Okay, so we started to look at the interactive methods. So previously we saw some direct methods for computing, for solving the Ax equal b problem, the system of equations. Usually what happens is that not in all the cases you can use direct methods. So interactive methods are pretty useful and actually are something that fit very well in the computational scheme. The solutions may take one step or longer. And so one concept that arises here is the convergence. So how long it takes the iterative method to reach the solution that we are looking for. And the idea is that we take successive approximations until we get closer enough to the solution, and how close it may be determined by the accuracy and precision that you need to have. So in particular, typical converge to machine accuracy in much less time than direct methods is expected when you have large problems. Okay? One particular case that is a very interesting one is what is called Krylov Subspaces. So this falls into the category of interactive methods. And the idea is we have again the system Ax equal b. And now we are going to construct a new subspace. Let's call it K. And the idea is you start with the vector b, independent vector b, and you start to apply iteratively the matrix A. So you create b, A, apply to b, A squared applies to b, and so on. Okay, and the idea is if the problem is well posed, you have n-dimensional space, so you apply n-1 times the matrix A to B. Why we do that? Because you can show actually that by doing this operation, you will converge to the eigenvector of the problem with the largest eigenvalue. It usually is slow and only get you one eigenvalue, but I'm going to show you at the end that there are some cases where you can actually apply it. In addition to the Krylov, well, other applications are that you can use this for orthogonalization of the system, something like Gram-Schmidt or Householder to project other components. And also you can start with a random vector B. The bad side of this is that sometimes, depending on the problem, it may be non-numerically stable. Okay, so one needs to be aware of that. Another case based on the Krylov method is the Arnoldi iteration. It becomes if you have heard of that, it becomes the Langston's iteration for symmetric matrices. Basically, you take the orthogonal projection of the matrix into the Krylov subspace, and you construct this matrix H. The nice thing of this method is that it only requires matrix vector multiplications or vector-vector multiplications. Okay, so it doesn't require matrix multiplications as the Krylov subspace. And again, it can be solved. It can be used for solving the Ax equal b. Okay, I'm going fast here because we can go into details of these methods later if you are interested. Another interesting problem that comes with these interactive solvers is, and you probably talk about this while you did the root finding and minimization routines, is the conjugate gradient method. especially when you had a symmetric positive definite matrix. It works particularly well with a sparse system. The idea is basically the same idea that with any gradient method, you try to follow the tendency that the gradient is giving. So something like a steepest descended, but the difference that you apply to the conjugate. Okay. So these are a summary of different conjugate gradient methods applied to different cases. You have more information there. We mentioned something about sparse matrices last week. So matrices that have some particular structure, like upper diagonal or triangulars or in bands. We're going to see how that makes a difference. The idea is that if you have a sparse matrix and you have elements that are many of them zeros, you probably don't need to save the whole information of the matrix, and you can just save the elements that are not null. So we are going to see. So this is an example, for instance. This happens, and I'm going to mention this very briefly as well, because we are going to see this in more detail next class in particular. When you take a partial differential equation, you can discretize, or you are going to discretize the derivatives such that you can solve the problem. And when you do that, you are going to end up with something called a stencil that is nothing else than the matrix representation of the derivatives. So for instance, in that case, the second derivative of the quantity q, whatever it does, with respect to x, you can approximate, if you are assuming that you are doing center differences, like q in the next position minus 2q in the actual position plus q in the previous position, where position is something special, for instance, divided the delta square, delta x squared. So by doing this finite differencing, you can promote the derivatives into discretized values, and at the end, it will look something like that. So that matrix represents the stencil or the operator of the finite difference applied to the quantity q. So you can see the structure of the matrix is very simple. So upper and below the diagonal is zeros, and then you have three bands: the diagonal, upper diagonal, and lower diagonal, where there are no zeros. Okay, so this is a particular case. So this is something that happens several times when you're doing partial differential equations. So that's this case where basically you have a sparse matrix. Don't worry about this. We're going to look into this next class. We mentioned this also in the previous class, that try never to invert. And one of the reasons for doing that is, well, first of all, the inversions are expensive, but in second case, they also destroy sparsity. So let's take that banded matrix, and if you compute the inverse, you will see that it's a matrix full of non-zero elements. Okay, so you lost your structure there. Okay. You can try to also, so sparse matrices are very nice for doing LU decomposition, for instance. So you can see in that case, you can end up with two lower and upper diagonal matrices. So that's another reason why to try to keep that structure. Then how one can define if a matrix is sparse or not? Well, initially you can take the condition that it needs at least 10% of non-zeros to be dealing with a sparse matrix. There are some common formats, because they are so useful. There are some common formats for saving these sparse matrices. Compressed sparse row, compressed sparse column, of course, and then banded, which those are the best ones because they just store the upper and lower diagonals, and that's it. And you can actually define the bandwidth if you have more than the previous, the first and second diagonal. Okay, and there are several. So let me show you an example. Any questions before? I know this was kind of fast, but I want also to cover what we had expected for today. Okay, so this is an example of how the Google algorithm works, and I'm going to show you because it's a nice example of linear algebra. So the first step in this example is consider the internet like a graph, okay? A network with nodes that are connected. Let's assume that this graph is a stochastic matrix where each element in the matrix represents the connection between the nodes, being the number of nodes, the rows, and the columns. This is basically the algorithm. Then transform this stochastic matrix in the Google matrix. We're going to see what is that. And then let's find which is the dominant eigenvector of this new matrix. Basically, this is the page rank. And the page rank basically is the quantity that Google uses to order the searches that you get when you search for something. Okay? So let's assume that we have that simple network. And that network can be just web pages. Let's say U of T is the red node, and then points toward the blue node, which is the Department of Physics, and then the Department of Physics points to zeta, which is the green node, or the chemistry department, which is the 3 node, and so on. So these are web pages, and the links are the connections between the nodes. Okay. So if I want to represent this matrix, basically I look at the node 1, and then the node 1, I say by definition, is not connected to itself, but is connected to the node 1, to the node 2, it's not connected to the node 3, and it's connected to the node 4. And then I normalize. That's why there are 1/2. When I sum all the elements in the row, it has to be 1. Okay. The same thing happened for the node 2, node 3, node 4, and node 5. Okay. So a stochastic matrix is basically a matrix that is normalized either if you consider rows or columns. Okay, so it's clear. So it's a way to represent how the nodes are connected. Yep. Not necessarily, right? The Markov chain is basically a process where you don't have memory of the previous step. Okay, but basically it's what people call a connectivity matrix, if you want. Basically, give you an idea of how the network is connected, the topology. Okay. So we had this matrix. This is the previous matrix I just created. I reordered it in a different way, or I took a different network here, a different example, but you can see that the same rules apply now if I look at the columns. Okay, so it depends how you define the rows or the columns. But now, if I add by columns, this is it has to be normalized. Okay, so let me start with this vector 1, 4, 1, 4, 1, 4. Basically, what I'm saying is I took a vector that has the same probability of being connected to any of these nodes. Because the network has 4 nodes, I take 1/4. Okay, but it can be a random vector. It can have any value. I'm going to apply the matrix A to this vector. I call B0, so A times B0. And then I'm going to apply the matrix A again to B1. So it's A applied to B1, which is A applied to A to B0, or A squared applied to B0. Okay? So basically what I'm doing here is constructing the Krylov subspace. And why I want to do that? Because if I do enough times, I will end up with the eigenvector that has the largest eigenvalue. And why is that important? If you do that this enough times, you will end up with that vector in particular. This eigenvalue or this eigenvector will provide me the equilibrium state for this network. Okay. And basically, I can find which is the eigenvalue, and then I can sort all the possible links there. Okay. So depending on the discipline, you call this in different ways. If it is a dynamical system, this is equilibrium value. If it is linear algebra, it's a normalized eigenvector. But basically, the idea is that you can rewrite this system as the Ax equal B equation. It is in X, the vectors x1, x2, x3, x4, and then you end up with that solution for the system. In the same way, if you are doing probability, this is the random walk or surfer on the graph. So you can, the Google metrics I was talking before, it can be defined as this. Oops, sorry. And then the vector B is the solution for that system. So again, this is just an example of how kind of all come together, like the linear algebra concepts that we managed before or we reviewed before, and the Krylov subspace method that we mentioned before. Okay. Question? A transpose of the vector B. So instead of having the vector as a column, it's a row, such that the operation makes sense. There must be a typo there. It has to be a matrix. Yeah, Yeah, there should be another bit there. Yeah. So, yeah. Okay. So just a quick review. This is more or less what we covered last class and today. The idea is that you will find linear algebra concepts everywhere, partial differential equations, ODEs, linear systems like X equal B appearing in data fitting or graph problems, different kind of structures in the matrices, which is always a good idea to know about them. We are going to see this right now, why it's important, because according to that, we can improve our performance in the algorithms. Okay. The other thing is try never, unless that is really necessary, to invert a matrix. Okay. It will destroy the sparsity of the matrix, and it's usually something expensive and something that may run you into problems. Okay. So this is what we're going to see now. Any questions from this? I know that it was kind of fast from the previous class or today, the quick review. Okay, so next thing is application. So which things we had already in place such that we don't need to do linear algebra operations by our own. So the idea is there are several libraries already out there performing numerical linear algebra computations so that we can use them and don't have to implement all these methods from scratch. Why? Well, first of all, it's a way to reduce the errors and bugs that we can implement. Every time that we go, there is the chance that we implement a bug. Secondly, and perhaps more importantly, this library has been optimized and it has been there for a while. So they are probably, there are no more bugs in those libraries and they are really fast. Okay. And the other thing is that probably they have several methods that will be more useful for you to investigate than just trying to create your own. Okay. So let's review some of the packages that are there. The one that we are going to be using is netlib. It's maintained by one of the, so this is funny because this happens several times. Each of these packages is maintained by one of the different national labs in the States. ORNL, netlib, PETSI is Argonne, and then Trilinos is Sandia. So each is like they choose, they come. But basically, the same idea and the same concepts apply to each of them. The netlib one is interesting because it's probably one of the oldest ones. It has been mostly written in Fortran. Already has call for C. So the ones that we are going to use is BLAS and LAPAC. All of them are open source, so that's good. PETSI is mostly written in C++ and has PDEs and iterative linear solvers like the one that we just talked. And then you have Trilinos, which is a collection of more than 50 packages, which includes linear solver, preconditioners, and others. And if you are more interested in other ones, you can take a look at the links. Not necessarily. Unless that you have a functionality that clears, allow you to choose something that makes your problem easier to solve or faster. It should have something to comment about that, Francis?
Last means part.
Yeah, I will show you.
Also, should warn against that.
Yeah.
Of the past. Is the fastest. They all do.
Yeah.
So see, kind of relates. She is more of her.
Yeah. So most of them are using underneath those. So BLAS stands for basic linear algebra paper, linear algebra package or something like that. So those are the ones that provide the primitive type of operations like matrix multiplication, AX equal B solvers, those kind of things. And those on top of that, they build the other. But I'm going to show you, I think I have an example showing how does the Fortran and the SQL works in Blast, for instance. No questions? So Blast. Blast stands for Basic Linear Algebra Subroutines. Are interfaces for these routines. They have been tuned and they have been debugged for a while. So the main thing is that the higher order operations like matrix factorizations as well as Gaussian eliminations are defined in LAPACK, which, as Francis was saying, resides or uses in the back-end Blast. The notation is a bit cryptic, so this is probably a good idea to spend some time. There are 3 levels of functions, and sorry, the level goes in complexity. So the first level is basic operations like S dot, which is the product between scalars and vectors, or AXPI, which stands for multiplying a scalar times a vector and adding another vector. You will notice that S dot and SASP here are the names, and the first letter corresponds to the type, is the prefix. So S can be a single, a double, if it is a D, C is complex, or if it is a double complex, it's set. Okay, so the first letter of the function, it defines which is the type of the operation that, or the variables that you are operating on. The second part is basically related to the operation that you are promoting or doing. Like the dot, it's the dot product, or AX pi is AX plus Y. The second level of functions are, for instance, gaining in complexity, like multiplying a matrix with a vector. So again, the convention is the first letter is the type, like double, and then the matrix multiplication, or the first 2 letters identify the type of matrix. If it is a general matrix, there is no structure associated with the matrix, it's general, GE. If it is a symmetric matrix, SY. And then MB stands for matrix vector multiplication. Okay. The third level is matrix operations. So again, the notation is, this case is a single, is a general matrix, and matrix multiplication. Or if it is a triangular and complex, is CTR/MM for matrix. Okay, so it's a bit cryptic initially, but you will get used to it. The different matrix types that you may have is general for a general matrix that doesn't have any structure underlying. General banded if there are some bands in the matrix. Hermitian, triangular pack, symmetric banded, Hermitian banded, or triangular banded. Okay. So the question is, or probably you're wondering, why should we learn all these functions and use these libraries? Well, take the matrix multiplication alone, right? Basically, the definition is the addition of the product of the different elements in the matrices. We can be rewritten as a 3-4 loops nest, right? As simple as that. So it doesn't have, or it doesn't look to have any complexity at all. And basically, you can implement that. The issue with doing this is not, well, the issue with doing this is every time that we implement something, we have the chance of including a bug, but also its performance. So this is a plot that probably is an old plot now, but basically this plot shows the performance of implementing the matrix multiplication just with a triple loop, as we were doing before, and then with a best scalar code, best vector code, and the best vector and parallel code. So this is a code like a Scala pack that is also using multithread. But as you can see, just by using even the simplest one, the simple ones, you may get a factor of between 5 and 20 in performance. Okay? And then on top of that, other factors. More about Blast. netlib, as Razi was saying, provides just the reference implementations. In addition to these open source resources, you may have commercial resources. For instance, you are running on Cynet, you have MKL from Intel. AMD has his own implementation, ACML, and IBM also had ESSL. Most of the BLAS and LAPAC are Fortran functions, and they have a C interface if you use CBLAS or LAPAC. This is one of the simplest libraries that you can try to install in your own computer, and I will suggest you to do that because it's very simple. You just go to the GitHub repository, you clone the repository, and then you just compile, and it shouldn't depend on many other things, so it should be easy to compile, even for Macs. I'm not sure for Windows, but in Macs usually works. So it's a good idea that you install at least OpenBLAS so you can try your examples in your own machines. If you are doing in your own machines, then the other thing that you need to recall is to fill these variables, BLASinc and BLASlib. Those are the directories where you're supposed to install the header files and the libraries. Okay, so then you can export the library path in the LD library path, and should be easy to compile. If you are using Cynet, you don't need to do that. Just load the corresponding module. So use the module find command for using for looking for OpenBLAS. You will see that there are several options. You can choose, for instance, GCC threaded, and basically all these variables will be filled for you. Okay, questions? Okay, so this is an example. It's a very simple example. It's a vector that is going to be multiplied by a scalar. So the function in this case is d, because my vector is a double, and scal for scaling the vector with the scale. Okay. So I'm including IOStream just for output, and then cblast.h for having the functions of the BLAS library. Okay. I'm defining just a vector of doubles 1, 2, 3, a coefficient. Then I'm defining something called 1, which is an integer. Tell you what is that, and then the size of the vector n equals 3. Okay, this is an example of a direct Fortran call from BLAS, and you will notice some differences with the C call. The first difference will be the name. So in this case, is dscal as the name of the function, but then there is an underscore indicating that actually is the Fortran. The other difference is that you will notice the ampersand in front of each of the variables, and this is because Fortran passes by reference, so you need to include the ampersand there. And the way to call is the function is the size of the array, the scalar coefficient that you want to use for the multiplication, the array, in this case, is the beginning of the array, and then this one is basically the increment. So you could have an array and apply the scalar not to all the elements, but 2 of the elements, like the first and the third and the fifth and so on. So that is the increment. And finally, the other thing that I'm doing is just outputting the result. Okay, so the call is very simple, just calling the function. Yep. Yep. Yeah, and the other thing is that it destroys whatever it was in the vector before. So it returns the value of the multiplication in the same vector. Okay, all these functions usually work like that. It returns the value in the same vector that you are applying. I'm just being like quick and dirty here.
Is it?
Yeah. Okay. So this is the C interface. The only thing to notice here is the name of the function changed. So it's cblast underscore dscale, and then there are no more ampersands there. Okay, but the arguments means exactly the same. Okay, so it's very easy to use after you know what the function is doing. So probably the most complicated part is to figure out which is the function that you need to use for whichever operation you want to perform. Okay. How you compile this? I'm compiling just this in one line, so I'm including header files and libraries path in the same line. If I have my LD path, probably I don't need this, but because I let's assume that we haven't updated the LD path, we are including the header path and the library path, and then minus L open blast is just for the name of the library. Okay, then I run the code, and that's the step. Yep. Yeah, the compilation. Yeah, both. Notice that both codes are in C. Actually, this is C, not even C++. The only thing that changed is how you call this function, but basically it's the same. One thing that I will strongly recommend is after you know which function you are going to use, always use the main pages, because the arguments may vary a lot and sometimes are a bit confusing. So in this case, this function is apply a matrix multiplication. Always when they say the matrix multiplication, and in general with any other function, it's more general than just that. This operation, what actually does is allow you to multiply two matrices, but also to add a third one, and each of them multiplied by a scale. So there are more general operations such as matrix multiplication. It's like the generalization of the simple idea of the matrix multiplication. So in this case, you have two matrices A and B that can be multiplied by a scalar alpha, and also can be added as third matrix C multiplied by a scalar beta. If you don't want to do this, you just set beta equals 0, and the result will be stored in C. Okay, so it's allow you to perform like generalizations of the operations that actually mean with the names. That's why it's always a good idea either to check. So this is a good point of reference for finding which functions you want to use, but then using the man pages for the particular function will allow you to get insights about the arguments of the functions themselves. Okay. So something related to that, and let's take a look at any questions about this. So something related to that and associated with the arguments is you can see this function in particular has several arguments: transpose A, transpose B, MNAK, alpha, A, LDA, B, LDB, beta, C, and LDC. So you can figure out that A, B are just the matrices. Alpha is the scalar I was mentioning before. C and beta the same. Transpose A and transpose B usually are if you want to use the transpose or you want to compute the transpose when you're doing these operations. LDA and LDB stands for the leading dominant size or leading dominant array of the matrix A and B. And this is related to how the matrices are stored in memory. I don't remember if we talk about C being row major and Fortran being column major, but basically how you store these matrices in memory don't necessarily match how you logically imagine the matrix. So basically, if I had a matrix of 4 by 4 and I had the element 3, 2, 4, 2, 4, 3, 4, 4, and so on, I imagine the matrix like a whole block there. Okay? What may happen in memory is that not necessarily all the elements should be together. Okay? And usually the LDA refers, or the leading dimension size of the matrix refers a how long is the portion of memory that I'm taking to cover the whole matrix. In general, you can assume that this matrix, that the LDA or LDB is the same size of the matrix. But in some cases, if you want to just work with a sub-block of the matrix, you can redefine that. In other words, if you are dealing with the whole matrix, just leave it as the size of the matrix, n by n, or whatever it is. If you want to deal with sub-blocks, you can adjust that accordingly. Okay. This is another example applying this matrix multiplication. As I say, I'm not interested in adding C, so I'm going to set beta to 0. The code works in a similar fashion as before. I'm including C blast. I'm defining matrices of 5 by 5. That's why all M, K, and A are 5. The coefficient in front of the multiplication per se is 1, so I'm not doing anything fancy there, just multiplying A times B. Now I'm using dynamically allocated arrays, okay? Just choosing the size of the arrays and defining them. Sorry, choosing the size of the matrix and defining the matrices. I'm going to define the matrices just by a simple rule. If I go from 0 to 5, I'm just putting in each element I plus 1. Okay, just to fill with some arbitrary values, but you can fill with whatever you want. Okay. Same thing with B. So here I'm initializing both matrices, and then I'm just calling this time the C call of BLAS, the double general matrix multiplication. Okay, and let's take a look at the arguments. Oh, this is the other part that that come into place. Because we are doing with row major disposition of elements in the memory, we are going to use C BLAS row major. Okay, we are not interested in the transpose, so C BLAS no transpose for both matrices, and then the dimension of the matrices, the coefficient alpha, the matrix A, that is the size of A, the matrix B, the size of the matrix B, the coefficient beta, C, and the size of C. Sorry. Okay. And basically, after compiling, this is the output. As is the definition of the matrix A, definition of matrix B, and the product of the multiplication. And the product of the multiplication of both matrices. Okay. So if there is some bookkeeping in the arguments that you need to use. But basically, after you understand these ones, it's more or less the same. Okay. Questions? Yep. That is the way that we store the matrix. If it is dominated by the row or the column. So in this case, because the way I'm filling the matrix and the way that C stores the matrix is just row major. You need to change this eventually depending on how you formulate the matrix. Notice that in this case I'm using a. Let me try to explain this a bit better. So let's say I have a just 2 by 2 matrix. What I'm doing there is, you notice, I have only one argument in the matrix when I'm defining the array, right? So basically what I'm doing is I'm converting this into a linear structure, right? So it's A11, A12, A21, A22. But I could choose to do in the other way. So now I'm doing by row, right? I follow each row, and I follow each row. This can be also interpreted as A equal A11, A21, A12, and A22. That means that I'm choosing a column major representation. So depending how you do this, if you choose to do row major or column major, is the key word that you use here. Because I'm doing row major here, I'm representing each of the elements in this linear structure like that, then I choose the row major. So this is an important point because by storing that, we guarantee that all these elements are together in memory, in the layout. And that's why I use LDA equal the size of the matrix. Yeah. At least if you are doing operations in the same function. If you do different operations with them, doesn't. But it has to be consistent within the matrices that you're choosing. And my suggestion will be after you choose one formulation or one way to describe, keep it like that, because otherwise you're going to get confused through the code, through the project that you're doing. Okay, any questions? So let's see some examples from LAPAC. So LAPAC now, as we were mentioning, contains some subroutines for solving linear systems, like the X equal B that we were talking before. Internally, as we mentioned, it calls BLAS. So it's based on top of that. It supports the same data types and the same structures as before. So the notation is going to be pretty much similar. Again, even when they don't match necessarily, there are 3 different categories of functions: auxiliary routines, computational routines, and driver routines. And it has an interface with C provided by LabPAC-E. Okay, so there's more information there, but it's going to be better if we just look at an example. The idea is that the computational routines are designed to perform single specific computational operations. So it's not something more elaborate. But within the operations that you can perform are LU factorizations, transpose decompositions, the orthogonal decomposition QR that we mentioned, lower orthogonal decomposition, and more complex ones. Also symmetric and Hermitian and non-symmetric eigenvalue decompositions, SVA, singular value decompositions, generalized eigenvalue and singular value decompositions. So it's all packages of things that you can operate and compute from linear algebra. So this is an example, for instance. This is the typical AX equal B solver. In this case, you can see from the notation already it's double, a general matrix, and the solver is B. Okay? And the way it works is pretty much the same as before. You have the size of the dimensions of the matrices. The matrices, if we want to use pivoting or not, the other matrix and the information. Information is something that is filled with the result of the operation. So this is an implementation. Now I'm using LabPAC-E. I want the C interface. I'm defining my matrices of size 3 by 3. So in this case, LDA is going to be equal to the matrix size or length, and the same for the other matrix, B. Actually, B is going to be the vector, sorry. The information is an integer. It's going to have the status of the operation, and then the pivoting is a vector of the same size that basically tells you if you want to do pivoting or not in the elements. We talked about that last week. Here is the definition of the matrix. It's a even matrix 3 by 3. Notice the way I'm defining the matrix is as we talked before. Instead of defining a double array, I'm just taking one array, one-dimensional structure, and filling there the values. And this is, again, row major. Okay, so each of these elements or this line represent a row, but it's linear in memory. Okay. This is the vector B. And one of the nice things that this function provides is that it can solve multiple systems at the same time. So what I have here is, you can see the vector B has 6 components. It should have 3 components only, right? Because the matrix A is a 3 by 3. So this is the matrix A. Let me put right. 680 and 645 and so on. This is the vector of X that I want to solve, and this is the vector B. And the vector B should have only 1 or 3 elements, right? 402, 619, and minus 822. However, I can put 2 of these vectors, and the routine will return both solutions at the same time. So it's solving 2 systems at once. And if you have more, you can add more. Okay, so you control that with an NRHS. I don't remember what it stands for, but it's the number of independent vectors that you can set. Okay, that's why I have set this to 2. Okay, so that is kind of neat because you don't need to call the function several times, just from once. It does. Okay, so that's the definition of the independent vector, and then here is the call to the function. Okay, so again, as we used before, C blast row major. In this case, is LabPAC column major. Then the value of the size of the matrix, the number of independent elements or independent vectors, the matrix A, the large dominant value of the vector or the matrix, in this case is 3, the pivoting, the pivoting is actually something that returns to you. If it does pivoting for solving the system, it returns that vector of operations that you need to do to actually diagonalize or triangularize matrix. So it's something providing that information for you. And then the vector B and the large dominant value of it. Okay? And so this is the solution. When you compile again, just include the BLAST libraries and OpenBLAST, and then the solution, the vector of solutions, and the details of the factorization. So this is how the LU decomposition of the original matrix looks like, and the pivoting indices. So the operations that it has done for switching between the original matrix to this matrix. Okay. Questions? So we talk about these sparse matrices or non-dense matrices, like the ones coming from the stencil from a partial differential equation discretization, or any other matrices. So they are also supported. We quickly mentioned them at the beginning. So there are banded, like double general banded solvers, tridiagonal, or symmetric positive definite matrices. Okay, symmetric positive definite is any matrix that has all eigenvalues positive. So those are very common as well. So for a triangular, there are some extra parameters. Well, for the triangular, there are no extra parameters. But when you have a banded matrix, there are some extra parameters that you may want to define. For the triangular, it's pretty much the same. In this case, I'm going to define 5 by 5 matrix, 2 independent vectors as we did before. And now look that in this case, I'm going to take just the upper rows, or sorry, the upper diagonal and lower diagonal and the diagonal of the matrix. So I don't need to define the whole matrix. Okay? And then I have defined the vectors. In this case, I have 3 independent vectors. And then the call is kappa key, double, general triangular, and the solve. Again, column major, the size, the number of independent vectors. And now the difference is instead of passing the whole matrix, I just pass the lower diagonal, the diagonal, and the upper diagonal, independent vector, and the leading size of the independent. Okay, so this is one of the nice things of these specific solutions for particular matrices that you don't need to specify, you don't need to waste all the memory on that, and it will take advantage of all this structure. Compilation works in the same way, and the solution now returns 3 solutions because there were 3 independent. Okay? Questions? What happened with sparse matrices? Well, there are no de facto actually standard for sparse matrices, not as much as the ones with a particular structure like banded or upper or lower triangular ones. There are some things that you may try if you are dealing with sparse matrices. The nice thing is that the standard template library may have some utilities, but there is no de facto that has been established so far. So there are some references there you want to investigate a bit more. These are some useful links. So this has a lot of documentation and there is a lot of reading involved because you have seen that the number of arguments, that's the only tedious part that this has. It has a long list of arguments, each of the calls to the function. And each time that you need to use one of the functions, most of the things remain more or less the same. But sometimes you need to change, so you need to look into that. So there are some links for documentation. Okay. I think that we are mostly done. So basically, this is just a review of what we mentioned. But basically, the idea of today's lecture is that you don't need to implement all this method that we have been reviewing from scratch. These tools are already available for you in these libraries, and the only thing that you need to do is basically try them, install them, and learn how they work. Okay? Questions? Yep. These ones, not necessarily, but there is one called Scala Pack. That one will work for distributed. Yeah, so far this is just
Class.
yeah, so, yeah, that was what it was.
See.
Yeah. What I was going to say, you can do multi-thread, but not distributed. So shaded memory is also not this exception of Scala. So the assignment will be probably posted between tomorrow and Thursday. So it's just for you that didn't listen to this at the beginning and were wondering there wasn't assignment 6 ready, that will be together with assignment 7 and will be posted between tomorrow and Thursday.
So we're going
No, just a second.
Yeah, sure. Okay, I understand that the row major, how you feed the matrix.